Welcome back to this module on exploiting DLP using SIMD instructions. In this lesson I will discuss some special purpose SIMD instructions and how conversions between different packed data types are implemented. Here's on the right a kernel from the motion compensation module of any video encoder, in particular MPEG. Do you recognize this kernel? We saw it before some lessons ago. I showed it when I talked about branch prediction, when I talked about the importance of using a 2-bit branch prediction scheme for correctly predicting the inner loop. Actually, this is the same kernel, but now the inner loop has been totally unrolled. Why has it been unrolled? Because it's very performance critical. This kernel can consume, when compared to the scalar version with lots of branch mispredictions, etc., up to 70% of the total execution time of MPEG encoding. Especially, or maybe even only for this kernel, many SIMD instruction set architectures support an instruction that computes the sum of absolute differences between unsigned packed bytes. And this special purpose instruction, the SAD, is designed only and only to accelerate the kernel block match which is used in video encoding. This illustrates the functionality of the sum of absolute differences operation. We have two packed data types, one on top, one on bottom. We compute the minus of each of these corresponding data elements. We take the absolute value and we sum up all the absolute values, and the result can be placed into a third register, and in this example the result is 165. So this is an example of a special purpose instruction which has limited usage except this very kernel that it's supposed to accelerate. This brings me to the next topic in this lesson, namely the conversion between different packed data types. Intermediate results of computations often require a precision that is larger, that is wider than the data type used to store data in memory. So it requires a precision larger than 8 bits or larger than 16 bits. Let's consider, for example, this simple kernel here, which computes the arithmetic average of two images. It adds corresponding elements of the two images and then shifts the result right to 1, and this is stored in the new image as indicated here. If the sum of the two pixel values is limited and we perform saturation or wraparound arithmetic and then perform the division by 2 by a right shift of 1 bit, then the result will look nowhere near to our picture that we started with. This is not what we want. So sometimes we need to convert to larger data types in order to not incur an unacceptable loss of precision. So we need instructions to convert between different data types, between different packed data types. And they are also called pack-unpack instructions, for example in Sans-Fis multimedia extension, data premotion, demotion, etc., etc. Pack operations convert from a larger to a smaller data type. In other words, from a wider to a narrow data type. And they can either perform truncation or they can be saturated. In truncation, the higher order bits are simply ignored. And in saturation, that we saw before in the previous lesson, the values are simply clipped to the range of the smaller data type, so that 255 remains 255. Here I present in this table several MMX-like conversion instructions. unpack from byte to half word to word. Remember that Intel processors call a 16-bit quantity normally a word, but I assume the MIPS terminology, which calls a 16-bit quantity a half word to word to double. These instructions unpack the lower half from byte to half word, the half word to a word, or a word to a double word, and merge. What that means I will show on the next slide. Similarly, the unpack high, unpack the higher half and merge. And then we have the pack instruction with sign saturation, which perform packing and saturation, as I explained here at the top. This here illustrates the working of the P unpack low from byte to half word. These instructions unpack the lower half from both operands A and B and merge these in a third operand C, in the destination operand C. If B contains all zeros, then it corresponds to an unsigned unpack, because the free bits are filled with zeros. If B contains all ones and AI and element AI is less than 0, then it corresponds to signed unpacking, because the sign bit is copied into the free spaces. It can also be realized signed unpacked by multiplication, sign multiplication by 1, which is a trick available if there is no P unpack low byte to half word instruction available. Data promotion and demotion, or conversion, has, however, some disadvantages. First and foremost, it consumes execution cycles. The pack and unpack operation, they require execution cycles. Furthermore, it reduces the level or amount of parallelism by a factor of 2, because the unpacked data type is twice as large and contains twice as few elements as the smaller data type. To prevent that we have to convert, the special purpose SAT instruction is an example. There are other examples such as signed arithmetic. Some SIMD extensions even support average operation, especially for the averaging kernels, to prevent it. This concludes this lesson. Thanks for watching. In the next lesson I will discuss data alignment and data reordering instructions. Hope to see you back.